So we want you to make better games in Unity. We want you to write more efficient code. But unfortunately, we teach the opposite, because if you go to our site, you will find many tutorials for beginners which teach how to use game objects, how to structure your game and code into components. But most of you already know that having a lot of game objects in a scene, each with a bunch of components, each with an update method, is not really performant. I visit a lot of studios, and from time to time they say that they don't really use Unity in a proper way. So they don't use components and game object hierarchies or update methods in components. Like they use update managers for components, or they have their own lightweight hierarchies for storing data, and they kind of feel that it's not a Unity way. And of course they feel like this because we as Unity advertise that everyone should use game objects and components, and this is a common misconception, and we want to kind of fix this. Of course, you can use game objects and components, and this is fine, but if you are making a mobile game, you would want every last bit of CPU performance. And to do this, you really need to structure your code differently. So to fully utilize CPU and all its cores, you need first control over data and data layout, because you really want your data to be how CPU likes it. Also, you need multi-threaded code which can execute in parallel to use all the cores. And you would probably like to generate more efficient code. So we want to educate our users and teach them how to structure code properly. Next, we are introducing a new C# job system, which is a safe and efficient way to write multi-threaded code. And with the job system comes jobs compiler, which does a really good job in compiling the code of the jobs in the most efficient way, so it runs much faster. But to use all these new shiny technologies, you will really need to change the way you think about code. So let's take a look at an example of what kind of a performance boost you will be able to get. So this is a Boyd simulation demo. It uses CPU to simulate a bunch of Boyds which have like really simple rules of how to stay together, how to avoid collision, and avoid different other objects like this big scary shark. Also, you notice that I changed all the fish models to cubes. This is because my laptop is not really performant enough, and I want to show you the CPU performance and not how the laptop struggles to render all the fish. So right now we have 2000 Boyds, and you can see that we are running like well 60 FPS, and nothing is going on worker threads on other cores. And you probably start hearing right now how my laptop struggles calculating all the Boyd positions. Okay, let's add more. So right now we have 10,000 Boyds, and you can see that the frame time is like 60-70 milliseconds. And let's see what happens when we add jobs. So you can see that all the logic is now being executed on other CPU cores, and we get a significant improvement in the CPU time. So let's add even more. And right now we have 30,000 Boyds. You can see that even with jobs, computing all the positions of 30,000 Boyds is kind of a hard task. So next we'll enable C# jobs compiler. This is the contrast. So we're simulating the same number of boys, but you can see how less time it takes. The jobs are now super small. Even if we add 70,000 more, and we are now at 100,000 boys, you can see that we are kind of at like 30 FPS mark. So at the beginning we had 2,000 boys, and with all optimizations we're now able to calculate positions for 100,000 boys. This is super cool and really exciting. So let's go back. When I was saying about that you would need to think about your code differently, the first thing I had in mind is that you would need to think about your data differently. So right now, if we use game objects and components, like all the components are stored in memory somewhere. So this first component, next, the third component. So when Unity iterates over all the components, it has to jump from one memory location to another, and CPUs don't like that because they cannot use the caches properly. So CPUs like sequential data like so. When they can use their internal caches to store like a whole bunch of data, not just one component. So if we think about code in object-oriented terms, like most of us do right now in Unity, so we might have a code like this. So this is probably the simplest ever component, which has a speed property, and what it does is just every update rotates and transform with a specified speed. So if you, for example, have like 1,000 of them or 10,000 of game objects with a rotated component on every one of them, soon you will notice how slower everything gets. And this is because every update call has some overhead. And a long time ago I wrote a blog post about this. So if you want more information with concrete numbers and tests, you should really read this. So what can we do to avoid 1,000 update calls? Next, we can make a special class, a manager, which will get the update and manually update all other components. So you probably might have something like this. So rotator, we have a reference to a manager, which we, in this example, get via a static instance property. And we, like, each and every rotator component adds itself into a manager, and it's a manager's job to update, to execute logic, basically. So you can see that the manager iterates over all the transforms and applies rotation to these transforms. So in this way, we have a tightly packed array of transforms, and we have a tightly packed array of speed values. But the problem here is that the amount of code we have now, and it's even with like a bunch of stuff I omitted here because we don't really need this code here to see here. So of course, comparing this amount of code to this simple rotator class, you can see why it's tempting to write your code like this. But we can do better. So first of all, we can add some syntactic sugar to this, and here's where we will introduce what is called entity component system. So the idea is that we have a bunch of entities, be it game objects, we have components which store data, and we have systems for types of components which execute logic. So let's see, right now we have a rotation speed component which just holds data, and we have rotating system which executes logic. And we have this syntax sugar which is called tuples, and this system keeps mapping of like an array of transforms to array of our rotation speed components. So it keeps this tuples in sync basically. So, and every update, this onUpdate method runs, and we do pretty much the same as in previous examples. We take transform and apply rotation. But you can see that right now we have much less code. So the next evolution of this system is that we don't really actually need our data to be a component. So we can have this like data in a struct, and for current purposes we also can have special components which wraps this data and which we put on GameObject to be able to edit this data. So, and here you can see pretty much the same system as we had before, but like we have an array of rotation speed, and we, in a simple for loop, we go through all the transforms and apply rotations. So right now we have our data in a struct, and this is where we can try and change the code to use jobs. So instead of this code, which goes through all the transforms and applies rotation, we can schedule a job here which does the same thing. And let's see how the code looks like. So we still have a component system, we still have tuples with transform and rotation speed, but in onUpdate we create a job, we run a job, and here we have a job definition. So let's take a look at what changed. So first of all, we have this, like, instead of an array of transforms, we have this thing called transform access array, which basically a struct which allows you to access the native representation of transform hierarchy, which is tightly packed into a binary blob of data. The next, we, in update function, we create our job. We instantiate this struct. We set data, so it's delta time and array of rotation speed. We schedule it on array of transforms, and we do some other things to specify dependencies. We'll get to it later. So this is how our job looks like. Basically has an execute method, and you can see that it does pretty much the same thing. It just takes a transform and applies a rotation from rotator's component. Let's see how a simplest job looks like to understand this example better. So what is a job? A job, first of all, it is always a structure. It implements iJob interface. This is why it has a execute method, and we have all the code needed in for the job in this execute method. So all the data for the job must be specified here, and all the data must be blittable, so either primitive data types or structures of primitive data types. So we don't allow any classes, any reference types, so we don't have like any garbage collection here, and we are sure that we can, in the job, we can change this data and have no side effects. So here's a definition of job. We have an array of floats, actually two arrays of floats. We can specify how we want to use this array. So we're saying that here we want to copy data from source to destination, and to run our job we first initialize it with like array of floats, with like 500 of them. And to run the job, we just execute schedule method. We get job handle back, and we can use it to specify dependencies. Or if we need results immediately, we just call job handle complete, and the system makes sure that this job and all its dependencies complete synchronously. So you probably noticed these native array things. So these are native containers, because as I mentioned before, it is all about taking care of your memory. So we have a few of this: native array, native list, native slice, which takes, which is used to take like a part of like other container. We have a native hash map and native multi-hash map, and all of them have a very familiar interface. So for example, to create like a native array, you create it like this, specify how many items you want, and since this native array is backed by a native memory, we want to specify how we want to use this array. So here we use it as a temporary allocation, but if we want, for example, to use this array through different frames, through different job executions, we'll specify allocator persistent. So, and this array can be used as like native C# array set elements, but to get rid of it, you need to call array dispose, and be sure not to forget to do this, because here, as already mentioned, we have no garbage collection. And actually, if you forget to dispose like a container you used in a job, Unity will tell you about it. And this is one of the great features of the new C# job system. So here we had really simple job which implemented iJob interface, but we have a few others. So first one is iJob parallel for, which is basically a for loop which is paralleled into a bunch of jobs. So you can see we have here like the same source and destination array, but in execute method we are getting passed an index. Like we create it the same way, but schedule method signature is a bit different. So we say here that we basically want to iterate over 500 items with a batch size of 100. So basically, if we want to like, execute this job right now, we call same job handle complete. And there's a special version of iJob parallel for, but which works with transforms, and which we used in the very first example of a job. It's called iJob parallel for transform, and in execute method it gets current index and also current transform access, which is used to manipulate a transform in a container. So basically, if you want to make a job which changes transform positions, you will need to use this. So the next thing, which is extremely important, is handling of dependencies. Because in the very simple example, we just have one job, which is executed at some point, but in the most of real-life examples, you will have many jobs with dependencies, like this job must run first, and the second job depends on it. So here's how we specify dependencies. So in this code, we want to copy an array to array 2, basically to copy source array to temporary array, and after that we want to copy temporary array to destination array. And these are two jobs. So the first job, it copies source to TMP, so we schedule it like so. And the second job copies TMP to destination, and we handle it like so. Notice that we pass job1 handle here to specify that this job depends on this job. And this is of course what we need, because if we forget to specify a dependency, we might get not what we wanted. So the next very important thing is safety, because multi-threaded programming is hard. You can get many kinds of race conditions and memory corruption errors, but we want Unity to be a sandbox. We want to tell you if you make a mistake. We don't want you to spend sleepless nights trying to debug your code a day before a deadline, because this is not fun. And this is why C# job system is architectured in such a way that it will give you an error if, for example, you incorrectly set up dependencies, if you access the same collection in parallel jobs, if you deallocate a collection while it is being used, or, for example, forget to deallocate a collection after all jobs are complete. So with a C# job system, we want it to be impossible to shoot yourself in the foot with all kind of multi-threading errors. And when you do something wrong, the system tells you what you did wrong and how you can fix this. Pretty much the same as a senior programmer would tell a junior programmer. So this is all really cool, but we want to make it faster. So as I showed you in the example, we have a new C# job compiler, which basically takes a subset of .NET IL and generates highly optimized native code through LLVM. And we can do this because we have many restrictions on what you can and cannot use in a job. So to enable this compiler, to enable this optimization, you just put this attribute on your job definition and everything magically will run faster. And it's even cooler because we can specify how precise we want our calculations to be. Because at some point we might not need very the highest precision. For example, in the Boyd's demo, we don't really care if Boyd looks like a few degrees off, because we actually don't see it, but we care about how many Boyds we can have in one simulation. So you can specify the precision here. So right here we have medium precision. So we also have a new math library, which is modeled after HLSL. So you will get new types, new vector types, and a bunch of math functions, which probably are familiar to you if you used to write shaders. But the cool thing is that if you use this new math library, C# job compiler actually can generate much more efficient vectorized code. And the final question of course is when are we going to have this? So we split all the things into stages. So the first one is a C# job system, which we're trying to release by the end of this year in 2017.3. Component system and math library are actually just Unity projects, so we will probably release them earlier. And C# drop compiler, we are aiming at beginning of next year. But of course we are trying to have everything at your hand as soon as possible.